One more time with feeling, the joys of being a parent. Not only do you get to spill milk over your kitchen, you also get to deal with potty training accidents right when you start screaming. So, with that in mind, let's start talking about what we are going to watch tonight. First of all, let me tell you folks, I'll get rid of this again, and let me tell you folks about some of the things that we've got planning in the next few weeks. We're going to be doing a little bit of a new kind of an endeavor because we've got, I think, 10 new courses that we're going to be offering at PacSec. So we're going to be doing the third week of September a free sample. Guys, kind of like a dojo bazaar where folks who are interested in the latest training about information security can go and get 30-minute samples of courses and get short little trainings, all very valuable in themselves, and get a taste of whether the instructor's material is really right for them and what they're looking for. So if you're interested in that, subscribe to secwest.net Twitter, and we'll have some announcements about this training bazaar, and come and get a couple of days of training for free. And with that, let's go over to our first talk, which is from PacSec. These two gentlemen, well, first of all, I have to excuse the karaoke at the beginning. One of them, Andrea Mabretti, awesome fellow whose 30th birthday was the day that he was presenting this. So now you also get to see why no one has ever invited me to karaoke twice. But they are very bright, and one of the reasons we picked this particular talk is because it really brings into focus what is a very complicated vulnerability with speculative cache execution and a lot of very complicated timing. And at the end of this talk, you'll understand why high-resolution timers are really a weapon. It's a very, very great way to understand a very complicated subject, and these two guys are so smart, they make it look easy. So with that, let me... I didn't have time to edit this stuff because it was a long weekend and it was a complicated week. So we're going to try doing this on the fly here. So we'll cut to this first, if it works. And oh, it's being fussy. Okay, so now we enter the karaoke. So actually, I'd like you all to help me sing along here, because I just found out that it's Andrea's birthday today. So please, let's all wish him a happy birthday. Happy birthday to you. Happy birthday to you. Thank you. Happy birthday, dear Andrea. Happy birthday to you. Thank you. Thank you. Way to turn 30, like absolutely, and it's a good one. 30, big one. So I think I can predict this next talk will be very interesting. This is because this set of bugs is just the bugs that keep giving. So they're going to talk about speculative attacks. As you guys remember, Intell's been having all kinds of problems, and we've discovered that many of our processors have issues with security boundaries being violated about predictive logic and predictive executions. So they keep coming up with fascinating new ways to exploit that, and I think these gentlemen are going to tell us some more. Please, a big hand.
All right, good morning everyone. Ohayou gozaimasu. This is my colleague and my co-president. Here's some test. Check, 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 check. Check, check. Can you hear me from the mic?
No. Sorry.
Just one minute. And now?
Yeah, very good.
Okay, so good morning, ohayou gozaimasu. This is my colleague, Andrea Mabretti, co-presenter, and I'm Anil Kurmus. And this is joint work with colleagues from IBM Research and also from Northeastern University. All right, so in this talk we focused on exploitation of speculative control flow hijacks. This is a topic that's very dear to us because we see it a little bit as the future of exploitation, or it's a possibility for a future for exploitation, and this is what we would like to convince you also during this talk, and hopefully talk about the various approaches that we've taken along the way. So in order to break with the tradition of going through a fairly complex design and presentation and then only showing a demo, we'd like to start with the fun stuff and just show an attack that's actually working. So that's a speculative control flow hijack that we've developed called double BTI attack, double branch target injection. So here's roughly the setup, the threat model for this one. We assume we have one physical core, a CPU, right? And it has two hyperthreads, and on one of them is a victim process that's running with some secret. Secret you will not get me in this case. We have an attacker process which will be doing some speculative control flow hijack and leaking data byte by byte from this victim process. Right, we assume they're collocated. All right, let's go on with our demo. So Andrea is running this demo here with the two processes, and it starts leaking. So this is live demo, so it's a very reliable attack actually, and you can see it leaking byte by byte the data from the victim process. So of course it's not clear what we're doing right now, but during the presentation we will explain towards the end exactly how this attack works. This is a new Spectre event. Alright. So the agenda, as we said, is first to talk about how these attacks work. So that would be part of our Usenix Wood presentation. So we had an article, a paper presented this summer at Wood called Two Methods for Exploiting Speculative Control Flow Hijacks. And the other part of this presentation is how we get there. Because although those attacks are nice, it's very important for us to understand how we can develop these attacks and also understand deeply these attacks. So we have developed a tool called Speculator, and it's a paper at PacSec. So this one will be presented actually in December this year. So it's for the first time for PacSec folks we're talking about. So those will be the two parts of the presentation. But first of all, let me start with some background. So who knows what out-of-order execution is? Just a rough show of hands, yes? All right, quite a bit, that's good. So out-of-order execution is a mechanism, let's say performance optimization that superscalar CPUs have been doing and that has been researched in the 60s actually. Execution here refers to the pipeline state of the CPU, and the idea is that by executing instructions not in the order that was specified by the programmer, that we can gain increased parallelism. Right? So let me go through an example here. Let's assume here on the left that we have a sequence of instructions that are specified by a programmer, or by your compiler, right? Assembly instructions. And this is the CPU's view. Essentially, it's an internal CPU component called the reorder buffer. And the CPU will, of course, start to fetch one by one those instructions in the program order. And simultaneously, we'll start to execute those instructions. So because of out-of-order execution, the idea is that we perform those execution in any order. So it doesn't have to be in the program order, it can be out of order that those instructions are executed. And the only thing is, in order to preserve the semantics that are observed by the program, we need to retire or commit those instructions in the order that were initially specified. So that's what the CPU does. It commits them or it retires them in the program order that was specified by the programmer in order to preserve the semantics of the program. Right? So this is out-of-order execution, and it is what's behind all of what are called transient execution attacks. So we can classify, interestingly, transient execution attacks in two categories. The first category are fault-based attacks. So you know, for instance, Meltdown, Foreshadow, Fallout, Riddle, they can all fall into this category. And we think that these are not very interesting attacks, actually, for the reason that although they are super powerful, you can leak a lot of data with them, and quite easily. It's actually fairly simple to fix them in hardware. Of course, it requires a new CPU, but it's not a huge design change inside of the CPU to fix those classes of vulnerabilities. And actually, we've already seen Intell fixing some of those in the newly released CPUs. The other class of attacks are the speculation-based attacks, and we'll explain what we mean by speculation exactly here. And these are what you know with Spec v1, Spec v2, and so on. And we think that these are very interesting from a research perspective because they will be here for the long term. A little bit like buffer overflows have been lingering with us. We think that those will linger for 10, 20 years with us, most likely. And today I will go a little bit about the background of Spec v1 now, and later on we'll see Spec v2, which is basically the basis for our variant for Spec. All right. So Spec v1, also known as bounce check bypass. Let's assume we have a bit of C code here, right? It simply compares a value x, let's say an attacker-controlled value x, which will index into an array 1 here. It makes sure that x is within bounds, and then dereferences array 1, and then we have a secondary dereference. So let's concretize this example in order to see what's happening inside of the CPU. Let's say array size is 8, we have memory here, so that's our array, right? X equals 15 and is attacker controlled, as we say. So the attacker finds this piece of code inside of the victim program and executes it with the input x equals 15. So the CPU comes here, there's a compare instruction, right? And the CPU, in order to know whether this branch should be taken or not, needs the value of array 1 size. Except that we assume now that array 1 size is not in cache, it's not cache, so it needs, the CPU needs to go to main memory, and that's like 100 cycles, and it will take a long time. So as a performance optimization, it speculates. So this is where speculative execution comes in. It says, let me assume that this bounce check will pass, that this compare will pass, because array 1 at x, which is clearly out of bounds, and leaks, accesses some secret. Of course, at this point, it's not leaked yet, it's simply accessed. And this is where the second array dereference comes in. It's what we call a side channel send. So the second array that we assume is somewhere else in memory, but shared between the attacker and the victim. The second array dereference here will occur somewhere within the array at an offset that's dependent on the value, so C here, right? And the CPU will perform this access during speculative execution. Then, later on, once this has completed, speculative execution is completed, this state kind of stays inside of the CPU microarchitecture. and the attacker then proceeds to measure accesses into each of the cells of this array. It notices that those that are not cached, which was the initial state of this array, will be slow. That's what we expect, right? But the one cell that corresponds to the leaked byte is fast. So the attacker therefore operates a side channel receives and now knows that the value is C. By repeating that, you can leak many bytes and the entire memory of the program. All right, so that was Spec V1. We have another important component of the CPU called the branch target buffer, Spec V2. How does the branch target buffer work? It's essentially, so for us software people, it's a little bit like a hash table. It's indexed by the program counter that the execution is currently at, right? And it says, oh, at this program counter, it's likely that I jump to this target here. So let me give an example. We have some piece of code here. We have our memory here. Let's say that at address coffee, we have some value E that is not currently not cached, and we execute this piece of code, which is an indirect call. So we will jump to an address that's dependent on the value at the address, which is actually coffee in this case, right? And this is not cached. Again, the CPU would need to wait, and instead of waiting, it uses its internal component here, the branch target buffer, to guess where execution should continue. So here it looks it up and it sees that at address A it should go to target V, so it continues speculatively to execute at address V, and then eventually the load completes, it realizes it made a mistake, it needs to roll back execution, and this is when it will proceed executing at the correct address, at address V, right? And then what happens, also important, is that the branch target buffer gets updated. The new value for this target, the CPU records that it should rather go next time to the target E in order to be faster. All right, so that was the branch target. So now we can move on with our presentation. The first thing that we would like to answer, the first question that we would like to answer is how we can study these types of attacks, right? So typically, if we look at something like memory corruption, we have a lot of tools, you know. You can fire if you have a crasher, you can fire GDB or debugger and look at what's happening. But for speculative execution attacks, we don't have any tools yet, right? So this is what we're trying to, the gap that we're trying to fill with the tool that we've developed. So we need some way of observing what's happening during speculative execution. So what do we mean by that? So what are the requirements? So we need something that has high accuracy. We need to be able to tell which particular instruction is getting speculatively executed or not. We need some information about what's happening inside of the CPU. So are we issuing an instruction? Are we retiring an instruction? Are we performing a load? And finally, we need a way of doing all of this without interfering too much with the actual execution of the instructions, because if we do that, we're no longer observing what we want to observe, we observe something else, right? So these are the requirements, and in practice, to satisfy this, there are really two possibilities that we could find. The first one is to do what everybody has been doing, and is to use side channels to try to figure out this, but this is not very flexible, it has very much limitations in terms of noise, and it's also complex to deploy as a program. The other alternative is performance counters. So performance counters are nice features of many modern CPUs, but have been implemented mostly for performance reasons, so in order to understand what's happening at the microarchitectural level to debug performance problems. These will monitor execution very precisely and give us some nice information. So for instance, on Intell, we have 3 fixed counters that give us some generic information, and there are some programmable counters that we can specify to know more detailed information about the execution. So in the case of simultaneous multithreading, SMT, also known as hyperthreading in the case of Intell, These are 4, and without, if one disables SMP, these are 8 available to us, so it's significant for us. And of course, the problem here is that there's basically multiple pages of those counters that are available, and we need to pick the right ones for us. So what are the right ones? Essentially, the right ones are what we call speculative execution markers. A speculative execution marker is basically a special instruction or sequences of instructions that will be detectable by the performance counters. And those instructions, even if they do not require, will cause a performance event to be reported by the CPU. So we use these speculative execution markers as part of our core. So there are other tools that make use of performance counters in general for performance reasons. Most importantly, there's POC events. That's both a tool and a system call available on Linux that will give you access to those performance counters. It has two drawbacks. There's 2 modes of execution, and each of them has some drawback for this specific use that we want to make. The first one is the sampling mode, which is not very precise, so it fails the accuracy requirement. And the second one is the counting mode, which unfortunately poses too much overhead, so it disturbs too much the execution because it's basically performed in the kernel and this messes up the measurements that we get. There are other tools. There's Liquid, for instance, but it performs system-wide measurements instead of doing process-based measurements, which is what we need. And also others which suffer from similar problems. So therefore, we had to develop our own tool called Speculator, and Andrea here has been the main developer on Speculator, and he will carry us through Speculator and how it works.
Thank you. We built Speculator, and as Anil mentioned, Speculator is a tool that is based on performance counters. And what we do in Speculator to basically solve the problem of overhead is that we handle the MSR register through which you can configure the performance counters directly in the program, so we don't do any operation in kernel space, which was the main problem for perf event, because a perf event was, is meant for bigger workloads, and it's not meant for, observe like free instructions at a time, right? And so using the MSR register immediately, we can basically bypass this overhead. In Speculator, also we provide a way for the user to generate a series of tests, and each one of these tests has incremental instructions. So we can, the idea is that we can observe each one of the instructions, how they affect the execution, and in this case, speculative execution. Finally, Speculator supports 2 modes of execution. The first one is like test mode, the test mode. So we basically can write test a little snippet of codes, and we can go and observe corner cases, in the microarchitectural state, and see how these corner cases behaves in speculative execution. And the other mode is the attacker-victim mode, where we instead can observe and use an attacker and victim processes and see how an attacker process can affect a victim process and leak data. Okay, so this is a general scheme of Speculator. As you can see, has 3 main stages. We have a pre-processing stage, a runtime stage, and a post-processing stage. In the pre-processing, we have the snippet generation, as I was mentioning before, and basically what happens is that we have a JSON file that includes a list of instructions we are interested in, and then we have a template, generally an assembly template, could be also a C template, and we basically merge these two, and for each one instruction in the JSON file, we generate a new test, and then automatically we have a CMake build system that detects and compiles everything just to make it easier. The generic, this is an example of how the template could look like. inside the template we will have like a setup phase. This is done to attach basically the test to the MSR interface, so we can handle the counter within our test, and we will be able to start and stop and reset the counters as required. Then we will, of course, at some point start counters, and one of the generic tests we brought was, including a branch. So we will use a branch as a way to start speculative execution, and we will have like a snippet of code which is in the part that we make sure that is going to be speculative executed. Of course, to observe a speculative execution, we need to make sure that the branch will mispredict, because otherwise we will not be able to tell the difference between concrete execution and speculative execution. So, and the idea is that the snippet will be speculative executed, but then the branch will mispredict, and so it will just like go towards like stop counters. During the runtime space, what happens is that we provide a monitor, which is an orchestrator, which takes each one of the tests, and it has three different like jobs. So the first one, shown by the second arrow, is to set up the counters for us. So we have a JSON file where the counters are defined, the one we are interested in, and the monitor will just like pick one of the CPUs and will just set the counters we are interested in for that specific CPU. Then it's going to take each one of the tests and it's going to basically start the execution for that specific CPU, and we'll just reiterate this process like 10 times just to make sure that we have enough data. And the idea is that whenever the test ends, it will signal back the orchestrator, which will then retrieve in our like first stage here in the picture, will retrieve all the information about the performance counter and just stores them. Finally, we will then, we have like lots of iterations of the one specific test, and what we do, we just like do some statistical analysis where we basically remove all the outliers, clear outliers, because of course things might happen during our test execution. So maybe a specific test will will receive some context switch from the operating system and so on. So we want to make sure that these are not accounted when we want to infer any particular properties. And then basically we provide the report. The report looks like the following. So we just have, in this case, the report with two tests. And we have test number 1, test number 2, and we report each one of the counters with a standard deviation. The first 3 counters are like the fixed counters that Anil was mentioning for Intell. And then the last 4 are actually 4 counters that we picked for this particular experiment. Okay, so one thing that, as Anil said, we need like not all the counters are meant to observe speculative execution, because we need counters that do not require the instruction to be retired to actually be observed, to be bumped up. And what we found in Intell was like we have like one counter which is the micro-ops executed that could be selected by either the full physical core or just a single thread. And this counter gives us like just like gets bumped every time there is a micro operation in the back end of the CPU which gets executed. The idea here is that this counter doesn't gives us a lot of information because it counts everything that goes through the pipeline, but can be used to basically remove the outliers. So, because if we get like the operating system to context switch while we are running one of our tests, of course we will see like a bump in number of micro operations that are executed for that specific core, and so we can remove those. Then we found other counters which instead are basically binded to a specific instruction. So whenever a specific instruction is found in our snippet, each one of these counters will be bound to 1. And so we found like this single muller, that is ready to use a single precision floating point instruction. We found like this slow LIA, which is a LIA with like 3 operands. This one is a bit tricky because we also discovered that there is like a CLFlash instruction, the one that removes a cache line from the cache, which also is counted as a slow LIA. So in this case, you might, if your test also uses a CLFlash, you might be careful with this. And then finally, we found that this LD store forward, which basically counts whenever there is a store to go forward, which fails, basically gets bumped up. And these 3 instructions are an example of that case. So whenever we have these 3 instructions in our snippet of code, this counter will be bumped up. Okay, so we, once we build the speculator, we found these counters, we start to kind of look into some of the microarchitecture kernel cases. We have many more findings in the paper. This is, I'm gonna just show you one of those, just for time's sake. And so the first test we ran was actually a test to verify some of the information we already knew about the microarchitecture state. In this case, we tried to count the return stack buffer size. The idea here is that the return stack buffer, it's already, its length, its size is already known, it's given in the specifications, and we wanted to see if we could actually measure it. For who doesn't know what the return stack buffer is, basically it's a microarchitectural component that is used to predict returns. So whenever we have a return in our code and the return value on the stack is not ready because it's not cached, the CPU would use this shadow stack, which is something that the application cannot really see. It's self-managed by the microarchitectural state, and it's going to basically use it to predict where to start speculating. Okay, so to basically perform this test, we basically wrote this little snippet of code. So when we start to execute, we start from the entry point, and the idea here is that whenever we encounter a call, transparently the CPU will, of course, update the stack value with the return value, but also it's going to update the internal structure with the return stack buffer. So in this case, we just executed the call to victim, and an entry for victim is inserted in the return stack buffer. Then again, we have another call to this another function filler, and again, we will have like a new entry in the return stack buffer. And here, what we do in this filler function is we basically generated multiple snippets of the same test, okay? And in each one of them, we had a growing sequence of calls and returns. So in our first test, we had like 1 call and 1 return. In the second test, we will have 2 calls and then 2 returns, and so on and so forth. So the idea is that this sequence of calls, this growing sequence of calls, will just add the new entries in the return stack buffer based on how deep we want to go in the call stack. And the idea, okay, assuming that we reach the end of the buffer, and then we start execute all the returns, what is going to happen is that, of course, these values are then gonna be eliminated from the buffer. When we go back to victim, in our snippet, what we do is like we update the return value on the stack of the program. So we push, in our case, a new return value, this my exit in this case, and then we remove that value from the cache. We want to just delete it. The idea is that we want to reach this return, and we want to speculate at this return instruction. So at this point, the CPU doesn't know where to return because the stack value is not ready, so it's going to consult this return stack buffer. And it's going to find, in our case, victim, But as I said before, this is the old value, because the value on the stack of the program is now my exit. The idea here is that the CPU will start speculate at the original return value that found there, and if we put exactly there our marker, we will have a marker hit. Okay. This return is basically a load from the stack pointer, and this load eventually will resolve, will retrieve the actual value from memory, and the CPU will figure out that that speculation was wrong, because the new value that came from memory was pointing to this other function here, down here, called my exit. All right. And so now, this is the first part when we have a case where we don't fill up the whole buffer. What happens is that instead, when our sequence, our nested code stack, it's longer than the buffer size. So this is a circular buffer. So what is going to happen is that when we execute one more call, it's going to start to, from the beginning of the buffer, to add new elements. And at this point, we basically go and overwrite that victim value. Then again, we execute all the returns, so all the values from the return stack buffer will be deleted. Again, we update the value of the program stack, we flash it, and then we speculate the return. And at this point, the CPU will try to go in the return stack buffer, but that's now is empty, so there's really nowhere to go, because there's no value from the real memory, there's no value from the microarchitectural state, and so we will not see any marker hit. Okay. So given this situation, we can kind of compute now the return stack buffer size, which is in our case is going to be, in this particular case, is one entry for victim, one entry for our filler function, and then X nested call return, where X is the value where when we get X plus 1, we don't see any marker hit anymore in our performance counters. We use this test to infer for both the return stack buffer for Intell and AMD, and these are our results. So as you can see, this phase store to load forward is the blue line, and we have a change here from one marker hit to 0 around 14. And if we do the computation, we have, as I said, one entry for victim, one entry for filler, and then 14 basically nested call returns. And we get 16, and this is actually matching perfectly the value that the Intell provides as specifications. So this is basically to show that with Speculator we can get a precise measure at the micro-operational level. We then tested the same on AMD. We used a different marker, of course, because AMD has all the different set of performance counters. And as you can see, we have a transition from 1 to 0, to almost 0, but we'll explain later why, around 29 micro, nested calls. And here, if we do the computation, we get 31. When we got these results, we were a little bit puzzled, because if you look at the manual specification for AMD, the return stack buffer is actually marked as 32 entries. And we were like, okay, why we are kind of short of one? And we could not understand, we thought we had the flaw in our kind of methodology. But then we dig deeper in the developer manuals, and so it happens that namely AMD has 32 entries, but then one is reserved for internal use. And we believe that this is a circular buffer, so maybe they use that entry to kind of have a beginning of end, mark the beginning of end of the buffer. And so with Speculator we could actually get this precise value, which is the one that you could use from your application. Okay, so as I said, that we have other results. Refer to the paper if you are interested to see other information about microarchitecture. So now let's concentrate on the speculative control flow hijacks attacks. These type of attacks have 4 main steps. We have always an attacker injection. Okay, so with attacker injection we mean that the attacker poison the microarchitectural state in a certain way. It leaves behind some value in some of the components in the microarchitectural state. For instance, we can use the branch predictor, and we can train the branch predictor to, be able to predict something that we want. Then we want, to actually perform the hijack, and in this case, we want to lure the victim to execute a series of instructions that will use that poison value and for speculative execution, so that we can actually take control over speculative execution will end up. And finally, of course, we want to send this speculative execution to some place where we can leak some interesting value. And the idea is that we want to send it to a gadget that we call a side channel send gadget, which basically will leave some changes in the microarchitecture based on a secret that then the attacker can go and receive through what we call side channel receive gadget. So to give you an example here, this is a Spectre v2, like a schematization of Spectre v2. So we have our attacker here, our victim, these are collocated. And as I said, we start with a training, and what we do is we train this indirect call at location A. Given, and the target that we want to train is the location E. So we keep repeating this call over and over. And what is going to happen is that the branch target buffer will be updated with that specific value, because the CPU will start to believe that that's a very likely results for this indirect call. After this, we start the victim, and we expect the victim to have the exact same call, at the exact same location, and this. As previously we have seen, we want to be able to speculate this indirect call. So to do so, the target for the victim should be not cached. That's maximize our chances that that indirect call will be speculated. So when we reach this call, victim will find will start speculate and will start to use the branch target buffer entry that finds, and that is has been poisoned by the attacker. And the idea is that speculative executor is going to start using the value that finds, and is going to go towards what we call towards our gadget, which will be used to do the side channel send, and then we will leak through the side channel receive. So I've been talking about gadgets, side channel send and receive, but I haven't really gave any definition. So for a Spectre v2, what has been used as a gadget was actually a Spectre v1 gadget. So they redirect the control flow of the victim towards a double array access, and using this double array access, then they could leak, a byte at a time. The issue with this is that the Project Zero POC the people from Project Zero, they couldn't find any of such gadgets. So what they did was they used the JIT mechanism of eBPF to basically place that gadget there, and then they basically jumped towards that gadget. At this point, we question ourselves, can we find any other gadget? I mean, are there any other gadgets that can be used to leak information, or we are stuck with Spectre v1, which is notoriously very hard to find? And the answer is yes, there are other gadgets that can be used, and we found 2 of them in this work. And the first one is the instruction cache. So the idea is that if you can find a piece of code that is conditionally executed based on a secret, then you can observe this, if you can observe the same piece of code from the attacker, then based on how fast this function or this piece of code is executed, then you can have some information from the secret. And the second one is using the branch predictor. So during Spectre v2, we always had the attacker that was training the branch predictor for the victim, to poison the branch predictor for the victim. Can we do the opposite? Can we have the victim to train the branch predictor for us, for the attacker? So the idea is that if this is done based on a secret computer value, then we can, observing the behavior of the branch predictor, we can leak this secret value. Okay, going through like the POC for the instruction cache attack. As before, in Spectre 2, we have a training phase of an indirect call at a certain location, and this indirect we train towards like a location we would. Then we start our victim, and we will have victim to execute the same indirect call with the same offset. And if this indirect call with the same offset has at that moment of the call, the victim has like some secret in a register, what we can do is that we can redirect the execution towards this type of gadgets, where we have a comparison based on that specific register, and we will conditionally execute, in this case, a function 1 based on that value. So the idea is that, for instance, in this case, if RAX, if the secret is 0, we will not execute function 1. If it's different from 0, we will go and execute function 1. With this gadget, the attacker then will just need to go and execute the same exact piece of code and see if this code has been loaded in the instruction cache. And the idea is that we can then guess, some information about the secret. With this attack, we can leak just one bit at a time. And the requirements for this type of gadgets is that the function 1 that we pick should be a piece of code that is shared between the attacker and the victim. It could be a shared library, for instance. If we move towards the double BTI, this double BTI is the attack we have seen at the beginning of the talk. So it's the POC that I showed you right at the beginning of the talk. And it's divided into phases. It's a little bit more complicated, but this allows you to leak one byte at a time instead of like just one single bit. As before, we have a training phase of some indirect code, and we redirect the execution of this indirect code towards a gadget that contains a second indirect code. Okay. During this training phase, though, we don't want to have the attacker training also that second indirect code, because otherwise the branch predictor would believe that what is executing the attacker is going to be a very likely target for it. So what we do here, we just place a return instruction so that we prevent the attacker to go and execute that indirect code. Then we start the victim, and we have the hijack as before. At the time when we start to execute this indirect code, we will have a computed value in a register based on a secret byte. So you can assume like a program maybe is like executing and is like computing like some secret key or some password, and at some point we'll have like some secret in a register. If we can hijack a very close indirect call, what we can do is like we can use a second indirect call based on that register to add a new entry in the branch target buffer. And in this case, the branch target buffer will be updated with a new entry, and the target is going to be a function of secret. As I said before, the secret we expect is a secret byte. So the byte has 256 possible values. So this is like a quite short function. And then we will just need in the second phase of the attack to basically go and receive this value from the branch target buffer. And what we do here is that we again execute the first indirect call, and then we will also execute the second indirect call in the attacker. The trick here is that of course before there was a return, now we have a knock. And the catch is that the attacker would just go and patch itself just before, to switch between training phase and the reading phase. When we go and execute this indirect call, the value that is going to be used to guess where this indirect call is going to go is the value left by the victim. And as I said before, we have only 256 possible outcome for this function. If the outcome of the function is something that we can map in a program, what we can do here, we can lay out all these possible values as outcome within the attacker address space. So we can basically map each one of these possible outcomes, and we can put them as a landing point for a speculative execution. The idea is that then we will just, when we speculate this indirect call, only one of these landing points will be hit, and if we have an array access in this landing point, then we can leak the byte by simply timing the array access. Okay, so we mount both of the attacks and we study them, and these are the results. They both work very, very well. In this case, to leak one bit. In this case, it's to leak 1 byte. Here we tested it on multiple architectures. As you can see, like the success rate is pretty good. Okay, we also look into the current mitigation, because Spectre v2 has been out for a while now. There have been mitigation for this type of attacks. The two of the mitigation, IBRS and IDP, defends like kernel code, high privileged code from user space code. But in our attack, the two processes are user space processes, so they do not really do anything for our type of attacks. One of the mitigations that actually works against this type of attacks is the IBP, which takes the branch target buffer and split it between the hyper threads, so that we cannot perform any poisoning anymore. The problem with this is that, in theory this works and it's very nice, but STIBP is very expensive in terms of as a mitigation, and is by default left as conditional, which implies that the user application has to request to have it as a protection, either using a seccomp or a PR control, the PR control interface. And most of basically all of the applications we have seen that don't use the seccomp are vulnerable to this, because nobody actually requests this type of protection. Finally, red polling as a mitigation for indirect calls would work, but the problem is that you need to recompile each one of the applications and each one of the indirect calls with red polling, and this hasn't been done yet in user space for user space applications. Okay, as a conclusion, we introduced these two new side channels and gadgets, and we tested them using the first BTI attack as a control flow hijack. The idea is that these are gadgets. We found these two gadgets and we tested with BTI, but they would work in theory with any other type of control flow hijack, speculative control flow hijacks. For instance, there is another type of attacks that instead of targeting an indirect call, we target returns, we could hijack the returns like a return to spec, and our gadgets would work also in that case. Through the cache, we can leak 1 bit at a time. Through the double BTI, we can leak 1 byte at a time, as we could see from the POC at the beginning of the talk. And the signal in this case is very good, because what happened is that we handle all these last array access all in the attacker. So what this means is that we can make sure that each one of the cells is completely evicted from the cache in a very easy manner. And so when the attack succeeds, we exactly see only one single signal, and it's the correct one. Otherwise, we don't. If the attacker doesn't work, then we don't see anything. So it's not that there is noise in the channel. And then, as I said, even though there are mitigations that would prevent this type of attacks already, but these are not enabled unless the application requests it. And as far as we've seen, and lots of applications, they are all vulnerable. And again, we will then use Speculator to mount this type of attacks. We first use the performance counter to verify that we were having the control flow hijack working, and then we could just switch to actually make it realistic using a final cache side channel or other ways. But the idea is that using the markers, you can have a first step where you can make sure that all the hijacks works, and you can build up upon those and more information. Okay, with this I conclude the talk. If you have any questions, Speculator is open source, so please go and use it, and feedbacks are always welcome. Thank you.
Thank you very much. That was amazing. That was the best explanation of speculative attacks that I've ever seen. It's very, very clear. They say that people who really understand it can explain things simply, and I think you guys deserve a second hand here, because that was really, really great. Any questions?
Great stuff. I wonder how common these gadgets are in code, because apparently you need shared pages across attacker process and target process, right? So you can't really control instructions. But how common these gadgets are?
So, in the case of the double BTI, actually, that's what's nice. So in case of the existing spec v2, you need a shared array, right, as we showed in the first, also spec v1. In this case, for double BTI, you don't need a shared array because the shared component is the branch target buffer, right, that leaks it. So that's one of the things that makes it a little bit easier to find. So in terms of practically looking for gadgets, we've started looking at them, and we found a bunch, actually. It always depends on how you're going to use them in a practical attack. So we said, let's mount a real attack on SSH, for instance, which basically you could mount a real attack on SSH. We looked at it. It's not using the ACIDP in the context where you could leak some data, some private keys, and so on. Except that in the middle of it, we found some other variants, and we got sidetracked, and we're working on that right now. So we don't have an attack on SSH that demonstrates that you can really use those gadgets, just because we found more interesting stuff to do, right? But we think that it should be possible to find those attacks as part of real, full end-to-end attack.
Other than just a few per process, so is that tens or hundreds?
So it depends on which type of gadget you're looking and so on. It's really more in the thousands and thousands range, but of course you cannot use any of them because it depends on the register values and so on, those that you want to leak, the bits and so on, the context. So you have to, and this is where an actual attack matters, because you have to say, I'm making this particular register, so I need this type of gadget with these bits. And yeah, but there are a lot of gadgets that are similar to this. As you can see, they are not particularly strange pieces of gadgets. Something that you would expect to see very often, both for the iCache model and for the double BTI.
Yeah, for the double BTI is an indirect call, right? So if you have an indirect call in a location where you're handling a secret, then that's totally fair game.
Follow-on question to that: do you see do you think it's potential feasibly to automate the search for the gadgets?
So it's certainly possible. However, we think that there are some difficulties associated with it, and we think this is basically another project on its own.
Yeah, because you kind of need to define in your searching tool what's is a secret, right? And that's in general in a side channel world, it's always like a problem with defining what you want to leak, and so once you can have like a simple like a raw gadget kind of methods, mechanisms to collect all of them, but then you will still need to go to some of them at least to verify that they are in a location where a secret, it's or what you are interested in to leak is close by.
So, in other words, a fertile ground for future research.
Yeah.
Thank you. Any other questions?
So you mentioned that STIVP and red pulling is possible mitigations, which are heavily costing components, which is why they aren't enabled by default. Do you have any idea for future mitigations which do not require architectural change with Intell and AMD?
So your question is, would there be defenses that do not require architectural change, but
Yeah,
would also be low performance overhead?
Yeah.
Is that? I think that's unlikely. I mean, it's hard to tell. I mean, red polling is fairly low overhead. Actually, just it's a little bit inconvenient to recompile the application. Comparatively, let's say it's still significant. Rather, at the microarchitectural level, we think that there can be changes in the future that will help a lot. For instance, for things like branch target injection, but we think still. Even with that fix, we think there will be other ways of having speculative control for hijacks that will remain relevant. Right?
Okay, thank you.
The whole class will be hard to mitigate, we think. There will be some mitigations, probably less expensive ones than the ones we've seen so far. Just to give like some rough overview, there's research on trying to do static analysis or fuzzing or symbolic execution to find SpecV1 type of code, and then you can selectively disable those pieces of code that are vulnerable in your application, so you incur only a low overhead on those particular ones, right? But yeah, it's an ongoing area of research, and this is why we think that there will be a lot of work ahead.
Okay, thanks. Thank you very much.
Thank you. One now naive question. I mean, you guys are focusing on Intel and AMD architectures. Is there similar branch target indicators in other architectures that could also be exploitable?
So speculative execution in general, it's across architecture, right? So a lot of the things presented here are not specific to Intel, AMD, and you can find this on other architecture as well. Not necessarily all, but it's super scale.
Yeah, I mean, they're all very similar in terms of like internal components and so on, and the way they implement stuff. So
the one case where you have differences is more on the meltdown, the fault-based attacks. These tend to vary a lot more across architectures.
Thank you. Any more questions? Good stuff. Last call for questions. Go on. Go on. Please, a giant hand for these folks.
Okay, so that was interesting and educational. Hopefully you watched that. And I found it one of the best explanations of Spectre and some of the techniques that are needed there. So with that, let me say goodnight to you folks, and remember to look at PacSec and the tickets that we have there and are going to be coming up in various languages, because we're going to be doing simultaneous translation, hopefully, into multiple languages. So with that, see you next week. Let's stop this stream.